Welcome back to another Kirchhoff's law. Today we are going to talk about Kirchhoff's voltage law, or simply KVL. I am Fatima from the EC department of the University of Utah. In nature, voltage is very similar to altitude. In other words, the changes in voltages is very similar to change in altitude. So now let's see what happens in nature when we change altitude. Basically, if you move in a closed path or in a loop and climb to the top of the mountain, the change in altitude that you go up is equal to the negative of the change in altitude when you come down. Basically, if you move everything to one side of the equation, the change in altitude when you move in a closed path or a loop is equal to 0. And that is exactly the same as KVL. The change in voltage when you move in a closed loop in a circuit is equal to 0. So there is something in here that we need to be careful of. You see, the direction of the movements in here matters for the sign of altitude. In other words, if, for example, you start at altitude 500 meters and you go down to 170 meters, the altitude drop is equal to 330 meters. Notice, this is the drop rather than the rise. That is why we say altitude drop is 330 meters. But if you move backward and you climb to the top of the mountain and you start from 170 meters and go to 500 meters, now the altitude drop is minus 330 meters. So it seems that the direction of our journey in here matters in the sign of altitude. And since voltage is very close to altitude, it seems that we need a system to make sure our KVL is working. Let's show you a very simple system with 3 steps to make sure always KVL works in your circuit. First, move clockwise in circuit. Second, for unsigned components that you reach to, such as resistors, choose the polarity arbitrary. It really doesn't matter if you put the positive first, negative second, or vice versa. You may want to have a preference, but it's okay, it's up to you. If you don't, it really doesn't matter. It's not gonna mess the law. And the third rule is, for all the components, signed or unsigned, use the sign you enter to when you're writing your equation. So let's start at this point. So now we have reached power supply. And because we are entering to a negative sign, we just put negative Vs. We continue our journey in this loop and we reach resistor 1. Arbitrarily, I want to choose to put positive first and then negative. And because I am entering positive, I just put positive V1. Okay, R2, I choose it arbitrarily. Now I choose to put negative first and positive second, and I have minus V2. And now for R3, I choose to put positive first and negative second. So I have positive V3. And when we go to the place where we started, the summation of all the voltages should always be 0. Now let's show this with a practical example. This is a schematic of a circuit board we made ready for you, and we are going to measure the voltages across all these components. And this is a board that we built for you that follows exactly the schematic at the left. All right, as you see, the board is the exact one as you saw in the slides. This is the schematic, and we have a power supply here, 1K, 2K, 2K, and the wire is just a circuit loop, and we are going to measure all the voltages and see if the summation adds up to 0 or not. For measuring voltage, the polarity does matter. If the negative sign is first, we are going to put the negative one at the first place, and then the positive one, the second one, and we see we got 5 volts. But since we have already written negative and we put the negative lead of our digital multimeter at the first place, then you need to write minus 5 volt. So let's do this again for the other resistor. In here, the way that we designed the boards, Pink indicates positive and blue indicates negative. For the power supply, this is across resistors. And for power supply, black indicates negative and red indicates positive. So for this resistor over here, let's just arbitrarily first assign positive sign here, and then the other side we just put negative. So we need to put the positive of our digital multimeter here and the negative of our digital voltmeter at the other side of the resistor. And we get almost 1 volt. And since we are entering with positive sign to this resistor, we just write positive 1. For the second resistor, now let's do this game and first write minus and the other side write positive. So when we do the measurement, we put the black, which is the negative lead of DMM, at the beginning of the resistor, and the other red one where at the pink is. We get -2, very good. But be careful, since we have already written minus at the beginning of this resistor, so we need to write -2, which is positive 2 volt. Okay, let's move on to the last resistor. Okay, now we put the signs totally backward. Let's actually put the positive of our DMM at the beginning of the resistor and our negative at the other side. So now we are getting +2, and since we are entering into the positive sign, this is how we labeled it, so we just write +2 in our loop. Although the signs are backward for these two resistors, you can see that we end up with exact same voltage for both of them. And this is what we exactly expect. Okay, now let's actually measure across the wire over here, which is our V4. Let's put positive here, and let's put negative at the other side. As you see, the summation of all the voltages in this loop ends up to become 0. That is perfect. It means that Kirchhoff was right in the KVL law, and if you move in a closed loop, always the changes in voltages, the summation is equal to 0. Thank you.